Lecture 51, Vector Integration. In that lecture, we discussed the surface integral, how to find the integration over the surface. Now, the surface integral. The surface integral is generalization of the double integral. So, let's suppose we have a surface. So, suppose this is a surface, and let P, we have taken a point P with any point on the surface. So, suppose that's in point P, and on that point P, there is a unit vector at that point, that is n cap, in the direction outward down normal to the surface S at P. So this is surface S and this is a perpendicular direction, that is in unit normal vector. Then the vector F in dot unit normal n is a normal component of the vector F at P, at that point P. Then the integration F vector F dot n cap over the surface S is written as double integral f dot n ds, and this is called the surface integral, or sometimes say the flux of the vector f over the surface S. So evaluate the surface integral. It is convenient to express them as a double integral taken over the orthogonal projection of a surface on the coordinate plane. So suppose that's in surface S and this is the projection of R on xy plane. So here we say R be the projection of S on xy plane, and on that plane the unit vector, that's a unit normal vector, that is I cos alpha, j cos beta and k cos alpha. So here that's an n unit normal vector n, that is it make the alpha angle from the x-axis, beta angle from the y-axis and gamma angle from the z-axis, if that's considered as z-axis. So here the cos alpha, cos beta and cos gamma are the direction cosine of that unit normal vector n cap. So here if we take the projection on xy plane, so the projection of ds on the xy plane, that is dx dy, is equal to, we write ds cos gamma. So we take ds cos gamma, and on the place of ds we replace ds is equal to, we can write dx dy upon cos gamma, and cos gamma is what, it can be k vector dot n vector, because corresponding to z, in position vector corresponding to z is k vector, and that is I, and that is j vector. So we can write k dot n cap. Similarly, if we want to value the double integral f dot n ds, so on the place of ds if we take the projection on xy plane, so we take that's dx dy upon k dot n cap. So that is used when we take the projection of the surface S in xy plane, and if we take the projection on yz plane, this is a, then we write dy dz upon I dot n cap on the place of ds. So that's in projection of on yz plane. And similarly, if we take the projection on xz plane, then in that case we replace ds with dx dz upon y square plus 4 by 3 yz. Now here that's in square. So here a dot a vector dot n vector is evaluated, that one. Now because we are taking the projection of that surface on xy plane, so here first we find that coordinates. So if we find the coordinate here, so that's point is 0 3 0. Here we put z and y 0, and on that point we get 0 6 0. If we put x and y in 0, so we get y 6, and on that point there is no need for that point, but if you put x and y is equal to 0, so you get 0 0 3. Now on that plane z is equal to 0 on xy plane, so the equation of that line is what, that is, if you put the z is equal to 0 in that plane, so the equation line is 6 minus 2x, y is equal to 6 minus 2x. So here we take a small strip that's in a small part of that region, and we, because we are taking the r, we say r is a projection of surface S, that is a triangle, that is LMN, that's in triangle. You see, that's in triangle L, M and N on xy plane, xy plane. So the region capital R, that is a triangle LMOLM, that is on that plane, that is the OLM. Now, so the is bounded, we can say is bounded by the x-axis, that's an x-axis, you see, that's an x-axis, and the y-axis, and that line, that is y is equal to 6 minus 2x. So which is bounded by x-axis, y-axis, and the line 2x plus y is equal to 6, where z is equal to, we take 0. So now we evaluate the integral, that is integration a vector dot n ds, which is evaluated on the region a vector dot n cap dx dy and k dot n. So here, because we are taking double integral, so the region a dot n is what, 2 by 3 y square 4 by 3 y z. So in that equation we put on the place of z, from the equation z is equal to 6 minus 2x minus y upon 2. From the equation of plane we put 6 minus 2x minus y is equal to y upon 2. So we put here, that is 2 upon 3 y square 4 by 3 y, and we write 6 minus 2x minus y upon 2 dx dy, and k dot n we get 2 by 3, 2 by 3. So if we first we simplify that, so we write double integral, and on simplification we get 4 by 3 y 3 minus x, and the limit dx and dy. Now the limit of x is what? The limit of x we take, if we take the strip parallel to the y-axis, so x is vary from 0 to, on that place 0 to 6 minus 2y, and y varies x varies 0 to 3, and y varies 0 to 6 minus 2x. So in that way we can say 0 to 3 is the limit of x, and 0 to 6 minus 2x is the limit of y, that's the limit of x. And now we take the integration of that. So what we get, we take the derivative with respect to y and then x. So we take the derivative with respect to y, treating x as a constant, so we get 4 by 3. Now you can easily evaluate that integral, as in you're using the double integration in the previous chapters. So when you evaluate that integral, this become, that is 2y 3 minus x dy dx. Here first you take the integration with respect to y, then x, because the limit of y is in the form of x, and after evaluating that integral we obtain the value is 81. You can easily integrate that integral. So please remember, first we have to take the projection of that surface on the xy plane. Now because we are taking the projection of that surface on xy plane, on that plane, so here what, z is equal to 0. So this point is what, 3 0 0. On that point, when you substitute the z and x is equal to 0, so we get 0 6 0, and that is 0 0 is 3. Now because we take the projection on the xy plane, so here we can say the r is the projection of the surface S, that is what, the triangle LMN. That's a triangle. See that triangle? This is the triangle LMN on the surface XY plane, that is LOM, that one. So we can say on the XY plane, the region R is what, is in triangle OLM, and this is bounded by x-axis, y-axis, and the line. So if you see that line, that's the line. Equation of line is what, if you put the z is equal to 0, so we can say this is 2x plus y is equal to 6, or you can say y is equal to 6 minus 2x. So this is the equation of line. Now here you see x varies 0 to 3, and we can say if we take the strip parallel to the axis, so y varies 0 to that line, equation of line, 6 minus 2x. So here we can say dy is equal to, or we can say 2y plus 2x is equal to 6, and here the z is what, 0 on that plane. So here in that, when we evaluate a dot n, so we get the z. So the value of z by the plane, we write z is equal to 6 minus 2x minus y upon 2 from the equation of the given plane. Hence the a dot n vector we get, if you put here 2 upon 3 y square, 4 upon 3 y, 6 minus 2x minus y upon 2, we get 4 by 3 y 3 minus x. Now we evaluate the integral, that is the double integral, that one, the double integration a dot a vector dot n ds is, we write integral the region a dot n vector dx dy, because we are taking the projection on xy plane, k dot n, and when we evaluate that, the double integral 4 by 3 y 3 minus x, and the limit of x is what, x is varies, as you see, x varies 0 to what, 0 to 3, that one, and y varies 0 to, you can say 6 minus 2x dy dx. Now you can easily evaluate that integral. First you take the integration with respect to y, then x, because the limit of y is what, in the form of x. So when you evaluate that integral, you obtain the value, that is 81, and that integral you can evaluate the integral. So here you have to remember one thing, when you evaluate a double integral, or we can say surface integral, so you always take a projection of that surface on particular axis or on a plane, Either you take the projection of that surface on zx, zy plane, zx plane, or xy plane. Now take one more example. Again, we have to evaluate the vector a dot n ds, where the vector a is zi plus xj minus 3y square zk, and the surface S is a cylinder, that is x square plus y square equal to 16, included in the first octane between z equal to 0 and z is equal to 5. So if we take the cylinder, so you see that figure, so we are taking the cylinder in the first octane. If we take, that is y, x, y, and that's take z, so the first octane, that should be the cylinder, and because that's in solid figure, so now here that's we take the origin, that's in we take that's a point capital A, that's we take capital B, and if you say that's A dash and that's in B dash, and if that's in origin O, so you can say that's an O dash. If you take that as O dash, so the first octane, the z, the limit of z is 0 to 5, so the coordinate are 0 0 5 of that O dash. Now as similar in the previous example, first we take a vector normal to the given surface. Suppose we say the surface is S, and what is that? That is x square plus y square minus 16, that's in surface. So first we take the vector normal. So the vector normal is what? Del S, that is the gradient of that surface. So how we find the gradient? So we take the gradient of that, that is del vector of x square plus y square minus 16, that is the derivative of x, is we get 2xi plus 2yj. So this is the normal vector, that is we can say n vector, and because we have to find the unit normal vector, so the unit normal vector is what? That is n cap is n vectors, and the we get 2xi 2yj, and here we get 4x square plus 4y square, and x square plus y square, we get what? 16, and we get 4, so we get 64, and we find that 2xi upon 4, sorry, we get 8, and 2y on 8j, or we can say the unit normal vector is x upon 4i y upon 4j. So this is a unit normal vector for the surface, that surface, cylindrical surface, as means the unit vector which is perpendicular to on that surface. Now here we take the projection, so either we take the projection of that cylinder on the xz axis, or you also take the projection of that surface, that's the curved surface, on the yz plane. So here we take, let's take the capital R be the projection of the surface, the curved surface, on you can take the yz plane, so we take the yz plane. Now if we take the projection of yz plane, so the double integral which we have to evaluate, a dot n cap ds, is we write the projection a dot n cap dy dz and I dot n cap, I vector dot n cap. Now we evaluate the first, we evaluate I dot n, that is I dot n vector. So the vector n, we are evaluating the vector n is this one. So what we get? X by 4i y by 4j dot I. So here we get x by 4. Now we evaluate the A vector dot n vector n cap, that is a unit normal. So the A vector is zi plus xj minus 3y square z k. We take the dot product with the unit normal vector, that is x by 4 I, y by 4 j. So we get 1 by 4 xz 1 by 4 and xy by 4. So here we get 1 by 4 x y plus z. So this is A dot n cap. Now here we find the limit, because we take the region, that is we take the projection on the yz plane. So the region is what? That's the region. So here the y varies from that point to B, and we can say the region is what? Here we write that the region is what? We take O B O B dash, O B O B dash. So the here it is enclosed by when y is equal to 0 to 4. Here y is 0, and at that point you can easily find, we get the point 0 4 0, and on that point B dash we have the it vary from 0 to 5. Very simple, there is no need to find that. So we can say z is vary 0 to 5. Now the integration, double integral A n cap dy dz I dot n cap is, we write double integral 1 by 4 x y plus z, and here we write dy dz by the value of that is x by 4. So that would be cancelled, and the limit of y is what? 0 to 4, and the limit of z is 0 to 5. Now both the limits are constant, so the order of integration doesn't matter. So you take the integration either first respect to y then z. So first we take the integration with respect to y. So we get y square plus zy, apply the limit 0 to 4 dz. So we get 0 to 5, and when we apply the limit we get 8 plus 16, that is 8 plus 4 z, that's y by 2. We get 8 plus 4 z dz, and on integration with respect to z we get 4 z square by 2, apply the limit 0 to 5, and on simplify we get the value 90. So in that way we can evaluate that integral, that is double integral A dot n ds. So you have to remember, when you are doing the surface integral, you take the projection either on the xy plane or zx plane or zy plane, because in that case we are taking only the projection on the zy plane, or we can take the projection on zx plane. We cannot take the projection of that surface on xy plane.